Hello, in this video we are going to look at the resistive biasing method. The simple biasing method was covered in a previous video, and the major drawback for that one was the sensitivity to beta. So let's see how the resistive biasing method solves this issue. So assuming I have on LTspice, first of all, I will put my transistor. Now place my transistor here. Then I press N for the voltage source. So this time I'm not going to put another voltage source for the bias VBE voltage. I'm going to ground this by pressing the letter G on my keyboard. Then I need to put a collector resistor here, below which I will tap the output voltage. Then another voltage for VCC. So I'm going to call this the microphone or AC signal. So instead of V1, I right click on the V1 and I type mic. Then I set the value, go to advanced, sinusoidal, and just as you have been using 10 millivolts peak or amplitude and 1 kilohertz frequency. So I'm going to wire it up. When you press W on your keyboard, you have access to the wire. Now I ground the VCC by pressing G. I right click to rename it VCC, and we set the VCC to 5 volts. As usual, we ground the emitter. So now let's see what happens. As we already know, if I run this transistor, I do not expect any results. Okay, one, I have not placed the value for the resistor, so I'm going to use 1K as we have been using all along. So I run it and I'm not getting anything because we know that the transistor is not biased. Okay, so now let's try and bias the transistor. So previously what we did was we put one resistor here, then we connected that to the VCC, and depending on the value of the resistor, the resistor's resistance, it drew some current which would be short-circuited to the microphone unless we place a capacitor to separate the DC from the AC. As we say conventionally, capacitor would allow AC to go through at the right frequency and the right capacitance value. The capacitor acts as a short circuit to AC signals, whilst it acts as an open circuit to DC signals. So we are going to, so that is proven by the impedance of the capacitor giving us 1 over 2 pi FC. So for DC signal, because the frequency is 0, we are going to get something like infinity, which is an open circuit. But for AC signal, depending on the values, we get an impedance, and it can be as small as possible when the frequency gets bigger or the capacitance gets bigger. So the capacitor, I set 2 micro. That might be a little too big, but we are not really interested. The most important thing we want to consider is we want to separate that. Later on, once everything is working, you can decide to optimize the size of the capacitor. Then we used in the previous video per our calculation, it was 400k for simple biasing, or 200k. I think it was 200k, but let's just see. So we have something which is okay. So the current through the resistor I cannot see the current through the resistor, but at least I can see the scope. So the current through the resistor I2, and it's only oscillating because of the AC signal that is coming in. So assuming I took out this AC signal, then I will just see the current properly. Okay, just to see the current flowing through, so I double click and go to my scope. I have not run it, so now I've run it. Then I see that the current through that is 10.56 micro, and that is given by VCC divided by R2. Okay, so that was for the simple biasing. Now for the resistive biasing, what we are going to do is, first I'll try and get some more space. So I press M on my keyboard to move the definition of the microphone signal, and the word mic 2 can move here. The value of the capacitor, I want to put it on top, so I have a lot of room down here. Now in this method, we try to limit the sensitivity to beta, because for the previous method that we looked, that is the simple biasing technique, our biasing was based on the IB that we got, and that gave us corresponding IC, which is IC times IB. So if we wanted a particular IB, we needed to set a particular if we wanted a particular IC, we needed to set a particular IB to determine the IC that we would get. But the IC was equal to beta IB. That means that if the value of beta is not what we intend, we might set the value of IB, but we will not get the intended IC. So beta 2 can change during operation when there is heating. So we want to find another method that is regardless of this beta. So a method that would rather bias the base emitter junction VBE by setting appropriate temperature. So assuming I desire IC to be 2.5 milliamperes to try and get my headroom in the middle, whatever gain that I get, I'm okay with that. Of course, I could also take gain into consideration. If I wanted to take gain into consideration, assuming I wanted a gain of 30, then from my design, I know that gain is equal to GM times RC. Our RC being 1 kilo, I'll divide my 30 by 1000. Then I have my value of GM, and from GM I will get the desired IC. IC is equal to 26 millivolts. Multiply both sides by 26. Let me just assume 24 for easy calculation. So it goes here 40 times, and I have my IC to be 0.75 amperes, which is a bit too big. That would be 750 amperes. So either I would have to change the value of my resistor or play around it till I got that. Okay, so that just tells us that we can use gain to determine the particular IC that we want. Of course, if we are still interested in that, then we could also have to increase the power So it makes sense that maybe a power of 5 volts, voltage source of 5 volts, would not be able to give us the required IC, the required gain, if our RC remains at 1000. Okay, so assuming we are not very much interested, we just want the headroom. So at rest, when the microphone is not giving any signal, what we want is the output voltage to rest in the middle, and a collector current of 25 millivolts will help us achieve this. So we are going to try and build this. So to do this, then if our collector current is 2.5 milliamperes, the next question we ask ourselves is, what value of VBE will give us 2.5 milliamperes? If we remember the formula, IC is equal to IS exponential VBE VT. Then I divide both sides by IS. Then I find the natural logarithm, which will cancel this E, and then I multiply both sides by VT. So I have the VBE that I'm looking for being equal to VT natural logarithm IC over IS. So I'm going to quickly punch this on my calculator and I'll write the answer. So VT is 0.026 times natural log. Then I have IC that I require is 2.5 milliamperes. So 2.5 milliamperes. So I have 2.5 milliamperes. So you need to pay attention to milli. Milli means times 10 raised to the power negative 3 over 10 raised to the power negative 14. Okay, so after doing my calculation, the value of VBE required is 0.6824 volts. So what I next have to do is figure out how to get this voltage across the base emitter junction by using a voltage divider. So I'm going to put another resistor here, and I'm going to tie it to the ground so I can connect it to this one. Okay, so after doing this, I could have also done this just to avoid any confusion. So just to clear your mind, this is the same as what I did before. So what value of resistors R2 and R3 will give me the desired base emitter voltage of 0.824? What I need to do is I have to meet two conditions. Number one, I want to use a voltage divider to divide the voltage 5 volts in such a way that the potential here across this resistor and the potential across this resistor will be such that here I'm going to get 0.6824 in the base emitter junction. Now before we do that, let's look at something which might be very interesting to us. Now assuming I just split the resistors into two. So first of all, per your input impedance, you want the value of these resistors to be big enough to satisfy the required input impedance that you want. Also, you want the current through these two resistors to be bigger, at least 20 times or 10 times the least bigger than the base current, so that you will have these two resistors approximately in series. So if our desired collector current, where we are starting from, is 2.5 milliamperes, then what will be the value of our desired base current? We know that beta is 200, so that's going to be 0.0125. Okay, milliamperes. So if we desire a current that is at least 10 times bigger than this, so 10 times might not be so nice, but let's just use 10 times bigger than this. Then in that case, the desired resistor, sum of R1 and R2, should be such that if I divide that sum by VCC, which is 5, then I'll get a current that is 10 times the base. Okay, so now let's see how that will work. This is taken as one term, then the base is going to be 5 divided by 10 times 0.0125, and what that gives me is 5 over 10 times 125 1 2 3 4 times 10 raised to the power 4. So I have my 5 cancelling this as 25. If I bring 110 out of this, 100, then I have times 100 again. Here I cancel this, I have 4. Then 2 can cancel this, I have 5. 5 can cancel this, I have 20. So what I am getting, which doesn't seem to look right to me, is 40. Let me just punch that on the calculator. Sorry for wasting time. So if I am to do 5 divided by 10 times, so 5 divided by 10 times 0.0125. Indeed, I got 40 on my calculator. Let me see what I did wrong. I don't want to believe that 40 should be the resistance. So VCC over the sum of the two resistors R1 plus R2 should be equal to 10 times, more than 10 times the base. And we desire that our collector is 2.5 milliamperes. So what will our base be? 2.5 divided by beta. So I'm going to divide 2.5 by beta. This time I'm using a calculator. I can no longer trust my mathematical skills at this point. So 2.5 divided by 200 is 0. Okay, so that is a trick. 0.0125 milli. So it should be 40k. Okay, so I forgot the milli. So the sum of the two resistors R1 plus R2 should be 40 kilo ohms. Okay, so if that is the case, how do I divide 40 kilo ohms in such that I will get a voltage of 0.682 at this node? So using voltage divider, if I have two resistors and this is VCC, which is 5 volts. Now I am ignoring the current that will flow through this branch. That was the reason why I made this current 10 times the base current. So I have an input impedance of 40, which is also good, 40k. That's 40 kilo ohms, because these two which adds up to 40 kilo ohms approximately, will be in parallel with the R pi. So 40k in parallel with R pi, the value should be around 40. The value should be around R pi, which is good. Okay, now what we are going to look at is how to get the voltage, so how to split between R1 and R2. So we are going to say R2 over the sum of the two, which is 40k, times the voltage you are sharing 5, should give me 0.6824. 0.6824. Okay, so I will just multiply both sides by 40k. Just multiply both sides by 8k. So times 8k. 0.6825 times 8,000, and that gives me 5460. So if I take 40,000 away from this, 40,000, take away 5460, 5460, then I'll be getting 345. So now I can split them. So it means that R2 should have a value of 34540. Then R3 should have a value of 5460. Okay, so now if I run the circuit, let's see if everything is in order. So first thing I want to check is my bias voltage. Do I have my bias voltage? Yes, it's around what I want, just that the microphone is pushing it up and down, so that is fine. So the operating point, if looking down here, you see that I have properly biased to get 681 millivolts. Then we look at the output. So the output, do we have some gain? Let's subtract the middle point voltage and see. So the middle point voltage is 4.97258. So let me take that away to see the actual output swing. 4.9827, so minus 4.9827. Okay, so I think I subtracted more than enough. So 4.97, let me just write it here. 4.97258. 4.97258. 4.97258. Yes, so I was getting enough voltage gain. Sorry, it worked well. So I just double right click this and take away 4.97258, which is the center voltage of the headroom. Did I do something wrong again? Because it looked like I had a perfect minus 4. 4.97258. 4.97258. Okay, so I'm not getting enough amplification. So let's try and go back to our circuit and troubleshoot it. So first of all, what current are we getting through this? The current we are getting through this, after double clicking, I can check. The current is around 25 micro. So let's check. And what current? 200 and the current was around, centering around. So let's first detach our microphone signal and debug, do some troubleshooting. Okay, so after troubleshooting, I see that the current is somewhere to 125 microamperes. Is it more than 10 times the base current? Let's see. The base current too is in nano, so it means that the base, something is not right here. Okay, another thing, let us look at the current through the collector. The current through the other resistor is also, so looking at it well, okay, so we have a current of, so if you look down here, we have a current of 1.125 microamperes coming through this resistor. Now how much of that current will pass here and how much of that current will pass here? Let's see how much of that current is here. So we ended up getting about 1 microampere passing through the base. That was exactly what we expected. So then why are we not getting the right? Are we doing something wrong, or we are not measuring the right node? So let's put our capacitor back. To you. Okay, so we look at our input. So our input is working fine. So this is before our signal is working fine. Then after the capacitor, we have the signal plus the DC bias, which is fine. Then the base emitter voltage sorry, the base emitter voltage as we expected. Okay, so sorry, I always make this mistake. The transistor, we should select this transistor to get the right values. So hopefully the issue was with the transistor. And yes, now we have something meaningful. So if I take the center voltage now, the center voltage